On April 22nd, 2021, a catastrophic engine failure on a 460-foot-long passenger and car ferry near Bainbridge Island, which is near Washington, started a fire that caused more than $3.8 million in damages. On March 14th, 2022, the National Transportation Safety Board concluded its investigation into the incident and tied the fire aboard the Wenatchee to an improperly tightened fastener. A single nut. The fire occurred during a sea trial in Puget Sound after the fastener failure led to components from the engine being ejected and causing a fire in the engine room. Luckily, none of the 13 crew members were injured, and their swift action prevented it from being worse. The issue dates back to November 2020, when the Wenatchee, operated by Washington State Ferries, was taken out of service for maintenance. During maintenance, 2 of the 4 main diesel engines were overhauled by factory-trained technicians. In February 2021, the crew conducted engine tests following the overhauls. Alarms went off in the number 3 main engine, and crew members found pieces of a cigarette lighter in the lube oil system. The maintenance technicians came back, drained the oil, and searched the lube oil system for 2 days. They recovered about 70% of the cigarette lighter's plastic and metal components and told Washington State Ferries that it was fine to run the engine. However, none of the engines were run again until the vessel headed for a sea trial. In April, during the post-maintenance sea trial, the connecting rod assembly in the number 3 main engine failed and ejected components that breached the crankcase and ignited hot pressurized gases. The crew contained the fire by stopping all fuel supply and ventilation to the engine room and isolating the space. One crew member witnessed, quote, "fire, smoke, and debris flying everywhere." Engineers examined the lube oil system to see if the cigarette lighter could have caused the engine failure. While they found parts of the lighter throughout the system, they found nothing that would suggest the lighter parts started the fire. The NTSB found that the probable cause of the mechanical failure was the connecting rod assembly that came loose due to insufficient tightening or torquing of a lower basket bolt during the previous engine overhaul. The NTSB stressed that maintenance technicians should use a calibrated torque wrench in compliance with the manufacturer's recommendations and verify that all required torque requirements had been completed. This is not the first time that improperly torqued fasteners have caused problems. A fire aboard the Carnival Liberty cruise ship in 2015, a fire on the Nanita bulk carrier in 2016, and an engine failure on the Red Dawn offshore supply vessel in 2017 were all traced back to bad fastening, according to the NTSB. The Wenatchee was built in 1998 and can carry up to 202 vehicles and some 1,800 passengers, so it could have been much worse. All because of a, quote, engine assembly error, or nut that just hadn't been torqued right. The operator cooperated with the investigation, provided recommendations to prevent future incidents, and is designing and installing a video camera system with fire and smoke sensors for the Wenatchee and other vessels in its class. I'm David Manti. Tighten those nuts.
Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mounts, and I'm glad that you've taken the time to join us today as we look at how or 3 different ways that we can use camo or technology to improve our fastening process. And that first segment there with the information regarding the bad fastening on the ferry really shows how you could take a very small component that may be worth a few dollars or so, and if it isn't properly installed or fastened or torqued correctly, it could lead to millions and millions of dollars of damage. Now, one thing to take away from this as well is make sure you have your cigarette lighter with you whenever you're doing an engine overhaul. But we don't know a lot of what happened regarding the actual blame or cause, but the human element obviously was a component to this particular error. And this is all part of some of the different manufacturing risks that are present. Now, we don't know if the error was caused by the person not using the tool correctly, or if the tool malfunctioned or didn't perform properly. But nevertheless, the human element makes up the majority of the possible issues that can come up during the fastening process. So anytime we can help to remove that type of element from the actual process, where we're giving the operator the ability not to make a mistake, can certainly help in improving our quality. Now, there's also, in this case, for the example that was cited here, there wasn't an actual over tightening of that, but they said it was an under tightened fastener. Obviously, with an under tightened fastener, that any type of vibration or shock can cause that fastener to come apart and fail. But over tightening is also a really big concern, because what we're looking for when we are trying to keep our components together by the use of torque is we're trying to create the correct clamp load that exists between the two components. And that clamp load is generated by the tensile strength of the fastener. And so as we apply torque, we're stretching that fastener to meet that correct clamp load that we are looking for. And if we go to too much, we're going to take the tensile strength to its limits. And if there's any type of shock or vibration, that fastener can fail and break as well. And so fastener breakage is, as we've seen in that example, would cause a catastrophic type of damage. And in most operations, if we do have fasteners that will be subject to breaking, again, any type of shock or vibration can cause that to happen if they are over tightened. And so we've used this clip before, but it basically is showing us that a fastener has a ability to be in an elastic region, meaning that as we apply load to the fastener, if we release that load, the fastener is going to return to its original state. However, if we take the fastener what would be past its yield point, meaning that once we get to any type of deformation in the fastener, it's no longer going to return to its rested state, but it will just simply break at that point. And so what this looks like graphically is going to be, we would run our fastener up to the yield point, which is our first peak there. And then as we apply more load, eventually we're going to get a failure. And everything from the yield point to failure is going to be the plastic region of that fastener. And everything below the yield point would be the elastic region. Now we want to make sure that we're using the correct torque to get the correct amount of tensile strength or clamp load that we're looking for that, but we want to make sure that it's below the yield point. And so often when you'll see operators using certain types of wrenches, you can almost guarantee that sometimes they're going to be up against the yield point when they do that. And we'll take a look at that as we look at our demo portion as well. And so if we do have fasteners that are breaking or causing components to break because of the over tightening, that's going to lead us to high scrap rates, and that's just a waste of time and money and labor. So if we can help to reduce that, that's always a win. And another risk is not having the ability to have an error-proofing process in place. We'll take a look at this as well when we look at the cam over style of tool. And then we also want to make sure that we've got the correct tool for the correct application. And so what does that mean? That basically we're looking at making sure that if we've got a very critical type of application, that we're using the correct and proper tool for that. not just any tool that is going to obviously provide us with torque, but that it is the correct tool for that application. And so all of that kind of encompasses what we're looking for when we're trying to handle and manage torque control, or our clamp load that we are trying to achieve with our fastening process. And so we want to make sure we've got the right tool, that we've got a good process in place, that we are delivering the right amount of torque to the fastener. And this is going to, again, help to enhance our process and reliability. It will ensure conformity, because anytime that we have variables within the process, that introduces the ability to have things go wrong, and we're reducing scrap rates as well. Now, is your quality process at risk? Well, let's take a look at how the 3 ways that we can improve process control with the use of a cam over style of tool. And the first one is to eliminate the operator influence. So in our example, the officials at the NTSB said that the operator did not fully tighten the fasteners. And so that type of, operation does lead to the human element. And if we can help to eliminate that within the use of a cam over, or a torque wrench, then we have a much better operation, or a much better chance of getting the operation done correctly, because we're using a tool that would implement an error proofing process. And that cam over tool is also a preset style of tool that enhances reliability as well. And that leads us right into point number 2, which is our preset torque tool. Now, using a preset tool helps to eliminate one of the variables that we would rely on the operator to go ahead and adjust the tool to the correct torque value if they're using an adjustable tool. If we hand the operator a preset tool, they don't have to think about it. They can just go use the tool, and the operation then has one less thing to worry about. Now, you can tell a preset tool versus an adjustable tool. Obviously, there's no scale on a preset tool. There's no adjustability of a preset tool. However, the tool is adjustable internally using whatever mechanism that may be used to adjust the tool, but a preset tool does have a range that it can be used at, but that tool is set and calibrated and verified on a torque analyzer to make sure that it's at the correct torque setting, and then given to the operator, and they can go ahead and use it at that point. So using a preset tool is always a good way to do that, and the cam over tool is a preset tool. And then our final and third point is going to be the torque wrench mechanism selection. Now, this we're going to take a look at a couple different examples of the torque wrenches, but those mechanisms make up how torque is delivered. And so all torque wrenches apply torque, but not all torque wrenches apply torque the same way. And this really is the highlight of using the cam over style of tool. So let's take a look at some of the other wrenches that are available. One wrench, the click wrench, is by far the most popular and most widely used and most affordable tool around the world that is used for applying torque. Now, the way that a click wrench works, we have our setting, we pull on the wrench, and when we hear the click or feel the click, we are supposed to stop pulling, and the wrench has delivered torque. Now, the issue with a click wrench is there is such a small degree of notification of when that wrench has actually clicked. That if the operator keeps pulling on the wrench, it is basically turned that into a static type of wrench, and they can add much more torque than what they were originally trying to achieve. And you may see operators out on the floor that will double click or sometimes triple click. By doing that, they are adding additional torque to the assembly, and we're getting into that area where we may be introducing over tightening to that particular fastening. And we'll take a look at that as we go through the demo portion for today. The next kind of wrench that you may see is going to be a breakover style wrench. Now, this basically gives us the ability to actually get a much clearer indication of when we have reached we've reached torque. When that wrench begins to break, then we have hit our torque value. So we get a much better signal of when torque is achieved with the use of a breakover wrench. And again, we'll demonstrate that in the demo portion as well. And then finally, we have our cam over wrench. And what this does, if you're not familiar with a cam over wrench, is once the torque is achieved, we're getting compression of the internal spring with our as we pull, and we're applying lobe pressure from the follower. Once we get to the point where the the wrench will simply cam over or slip, we will then be reduced to no torque on there. So the operator can go ahead and reattempt or try to torque that again, but they're never going to be adding more torque than when the cam slips. So the cam over tool is going to always give you the same torque value without the opportunity of over torquing the fastener. So for really critical type of applications, a cam over style wrench is going to be one of the best choices that you can use to make sure that torque has been achieved and it's been achieved correctly. So what are the accuracy of the different styles of wrenches? Now, with a click wrench, the signal or the click is kind of limited, again, to just 3 degrees of movement. And then we are adding additional torque to the assembly. So this does not prevent the operator influence by its use, and the accuracy can be at risk sometimes. Now, the click wrench is a very accurate type of wrench as long as it's used correctly. And again, if we want to try to remove the operator influence from that, we can do that with the use of a cam over style wrench. But there are a lot of factors that go into the use of a click wrench. Again, the operator needs to be paying attention. They need to make sure that they're pulling smoothly and at a slow pace. If there are demands to try to speed up production and get through things quickly, they may not be as precise as they may need to be, and that can cause inaccuracy readings for the use of a click wrench. The accuracies of a breakover style wrench are much better than a click wrench. The signal gives us a much greater much greater view of when we've achieved torque. We can go almost up to 90 degrees. In some cases, you wouldn't need to do that, but you do have that ability to see once you go past 90 degrees of break, then you'd be adding additional torque, but that would be very hard to do. So we get a much better visual indication, and we reduce the risk with a clear signal. So that may be an choice for you as well. And again, with the cam over style wrench, we're removing the operator influence from that. We've helped to introduce an error proofing process as we're relying on the cam to be the arbiter of when torque is achieved as opposed to the operator. And so they are precise and accurate with that. One other thing before we move to the digital wrench, the cam over style tool is also a non-length dependent type of tool, meaning that you can hold that tool anywhere up and down the handle, and it's going to deliver the same amount of torque that the tool is set to. And that's because the fulcrum point is at the end of the tool, or at the cam where the drive is. When we look at a click wrench or even the breakover wrench, those need to be held in the correct spot, or we'll be introducing inaccurate readings, because the fulcrum point on a click wrench is inside of the tube of the wrench, and it will be affected by our force and distance ratio. So we'll talk about that and show that too in the demo portion. So one wrench that we didn't talk about was a digital wrench, but again, a digital wrench is basically a static type of wrench that is going to signal, obviously, when torque is achieved. And there are certain ways that you can have the alert be given. It can be done either audibly, visually, or sensory. But again, there's nothing stopping the operator from adding additional torque if they do not listen to or hear the indication from the wrench itself. So again, nothing to prevent the operator from applying the correct torque with the use of a digital wrench. Now, all of these wrenches, again, may be the right tool for the right application, but if you are having problems with over torque and all that, then the cam over style wrench is going to be what you would need. And so that's going to lead us to our poll question for today. So as we go ahead and launch that poll, do you currently use any of these torque wrenches in your operation? We have click wrench, breakover wrench, cam over wrench, and our digital wrench, or finally a mix of those within that. So I'll give us just a minute here to go ahead and answer that. And I'll grab a drink of water and we'll go back into our demo portion. All right. Thanks very much for participating in our poll. Out of the standard answers that were not a answer of mixed, which was our highest vote, next would be click wrenches and digital wrenches. We didn't have anyone using cam over or breakover wrenches. So hopefully this information will give you a little bit more confidence in the process if you are looking for adding those types of wrenches to your process. So that's going to lead us to our demo for today. And, whoops, sorry. Let's see here. Okay, so what we have is our Easy Torque 3. And let's go ahead and power that on. Okay, so with this, let's add one more. We have our click wrench here, and we'll talk about how this the fulcrum point can adjust either length dependency or with the use of the click. And so, as you can see, the wrench, when it clicks, we just have that little bit of movement to release the wrench before we're adding additional torque to that. And so this head mechanism runs down inside here, and there is a little block that will go ahead and pivot, which is why it's called the pivot block or jump block. And this is what is creating the click. As we're applying load, the spring inside here will go ahead and it will cause the force from that to move that pivot block or push it up against the side of the wrench. So that's where we get the click from. Now, as we use this wrench, it's set to around 10 inch-pounds or so on our analyzer. Let's go ahead and set this to 10. And as we use it, you can see that if I pull it very slowly, I can get to 10. If I get too quick with it, I can add much more torque than what is intended. And this can really be seen if we change our mode. So right now we're in our peak mode. If I change this to first peak, what this does is it's going to capture at what point the wrench actually clicks. And then the smaller number here is going to show us the amount of over torque that happened with that. So in this case, we can see that the wrench, it clicked. Let's see here. It clicks at 10 inch-pounds, which is what we want, but we finished at 14.6 inch-pounds, which is what we don't want with that. And so, again, as the operator is using this tool, they may not necessarily be understanding what's happening with their use of this. We can also look at this graphically. So 10 inch-pounds is our target here. So the wrench clicks at 10.2 inch-pounds, but it finished at 18. And so if I do a double click, you can see much more torque has been added. Originally, the wrench clicks at 10, but we've got a max torque of 27 inch-pounds. And so this type of tool is a very operator dependent style of tool. But again, it can be very accurate if we pull it very with purpose or with with attention. It will get us to where we want to be. But again, we have to be very cautious when we're using that style of tool. The breakover style of tool, how this tool functions, again, as we apply load, this will begin to break. And so this would be at 90 degrees. Again, not very usable at that point, but what we're looking for is just when this begins to break, we've hit our torque value and we can go ahead and release it. There's also a groove here on the handle, which is where we're to put our grip. So we can do that. And so let's see where we're at here with this one, and we can adjust our mode. We'll go back to peak, and we'll see. So about 8.5. So if we set our target for 8.5, anything that's going to be in the green there is our within the specification. So again, we're getting a much clearer signal that when the wrench has reached torque, and we can go ahead and stop applying additional torque to that. So again, another way that we can signal to the operator that we have achieved torque. And finally, we have the cam over style wrench. Again, this is set internally. We can use that to either compress the spring in there. But as we use this, I think this is set to somewhere around 34. Set that to 34. And as we use this, oh, maybe not 34. Oh, 26. Okay, perfect. As we're using this tool, again, as we apply load, we can come and we can keep going, but we're never going to apply any more torque than the cam will allow us to do. And so, again, for really critical type of applications that you can use a cam over style tool on, that is going to give you the best results as far as controlling the amount of torque that's being delivered without adding additional torque to that process. And so hopefully that will demonstrate the use of the cam over by eliminating the operator influence, giving us a clear indication that torque has been achieved and that it has been achieved correctly and accurately by the cam mechanism that is the torque delivery system for this type of wrench. So that's going to lead us into our questions and answers for today. So with that, Chris, do we have any questions? So the first peak mode is used to calibrate click wrenches specifically. And because if we just used peak mode, so if we go back to the analyzer here, if we used peak mode for our click wrench, and I'm the calibration house doing this type of work, I could say, well, this wrench set at 10 is not very accurate. It's not meeting its actual torque output. So what calibration facilities will do is they'll use the first peak mode to calibrate the click wrench, because once that wrench clicks, it is clicking at the point at which the wrench is set. So we're not necessarily worried about what is happening with the any additional over torque, if there is over torque, because we just need to test where the wrench clicks. And so using the first peak mode is how click wrenches are usually calibrated. Now, this is also a great tool that can be used to educate operators when they're using a click wrench, to show them exactly how much influence they have on the operation. And so it can also be used as a tool. But typically when we're measuring torque for any type of tool, we're measuring the peak torque and the amount of torque that's being delivered. But for the case of click wrench, we'd want to use first peak just to see where the wrench is actually clicking. So we want to make sure that the spring inside of the tool is basically warmed up, so to speak, or exercised. So that is typically why you would exercise the tool to make sure that it's being in its proper using or its proper operational environment. So that's why we're just exercising the tool to warm up the spring. The standard is going to be 5, depending on the type of calibration that you're looking for. But it certainly can be whatever you may need it to be internally for your processes. But most calibration facilities are going to use 5 readings. So after the tool has been exercised, they'll take 5 readings to see, make sure that it's within the specification. If it is, then that tool will move forward. If not, then there are adjustments made, or if they're closer to the edge or of the scale, they may want to adjust the tool as well. But we do have also we have processes in place at other facilities or with customers that will take 10 readings, or they may take readings before the tool is used. So they may take 5 readings before the tool is used, go use the tool, then come back and take 5 more readings for really, really critical type of applications. So it just depends on your internal needs and processes, but for the most part, 5 readings is going to be a standard. All right. Thank you very much for joining us today. We look forward to seeing you next month. In our next month, we look at the key error or key ways we can help to error-proof the assembly process. So with that, thanks very much and have a great day.